Hi everyone, and thank you for attending today's webinar, Creating Intelligent Machines with the NVIDIA Isaac SDK, hosted by Cenk Oz Saglam and David Weicherstorfer. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple application widgets. All of the widgets, as well as the slide area, are resizable and movable, so feel free to move them around to get the most out of your desktop space. If you have any questions during the webinar, please submit them through the Q&A widget. We'll try to cover as many questions as possible during the Q&A portion, but if there's any we don't get to, please post them on the forum to keep the conversation going. Be sure to check out the resource list for links to the developer site, forums, and more. And if you run into any technical issues during the webinar, you can find answers to some common questions located in the Help widget at the bottom of your screen. An on-demand version of the webinar will be emailed to you later today. And with that, let's get started.
Welcome to the Isaac webinar. My name is Oz, and I am a software engineer in the Isaac project. We are very excited to have you here. Thanks for joining. Let me start our webinar by briefly talking about what Isaac is and why you would want to use it. Isaac SDK is the robot engine of Isaac family. It is a cutting-edge robotics platform for accelerating the development and deployment of robots. It is easy to learn and use, as we will illustrate in this webinar. It is a high-performance scalable software. It is robust, modular, and it is GPU optimized, ready for your computer vision and AI applications. You can find more details about Isaac on our website. In particular, you'll find a comprehensive documentation and concise overview from our director. A recording of this webinar will be available to you. I suggest trying Isaac out after the webinar. The material we'll cover today can be downloaded through the link here. 2019.1 is the first publicly available release of the Isaac SDK, and 2019.2 is going to be released at the end of June. This nightly build, which we'll use today, is a preview of what's coming in June. You can download it using this link. We would very much appreciate your feedback about this webinar and Isaac in general on our developer forum. Again, thanks for joining. One aspect of Isaac that I would like to emphasize throughout this webinar is how easy it is to move from test to simulation to reality. We'll cover all these steps in this webinar. Isaac equips us with various packages to make autonomous navigation look easy, no matter it is in simulation or reality. Let me show you what you'll be able to do at the end of this webinar. We are looking at a warehouse simulation from robot's point of view in Isaac Sim. Isaac SDK is capable of navigating robots autonomously while avoiding people and obstacles. No matter whether you simulate or deploy your application to a real robot, Isaac SDK provides you with a visualization tool called Sight. On Sight, you'll be able to track your robot's vision, localization, goal, and plan among other useful information. Using Sight, we can also change parameters. It seems the robot has already arrived at its location, so let's send it to a location we like. Let's go to the goal generator and change the desired Y position to, let's say, 42. When we hit Submit, we'll see that the robot starts autonomously navigating to the location that we send through the website. In this webinar, we'll show how to autonomously navigate a robot in simulation and reality to a location we like. We'll write the code for this goal generator that we just played with. We'll write the applications for testing, simulation, and reality. you will see that the modular structure of Isaac, navigation stack, and the subgraphs make moving from simple tests to a real application very straightforward. Now is a great time to look at the big picture. In this webinar, we will write this node, which generates goal or target locations for the robot to navigate to. And in return, it will receive feedback regarding its goal. To help testing, a mockup is supplied. Once we are happy with the goal generator, we will pull navigation and simulation subgraphs to obtain autonomous navigation in simulation. After confirming everything works as expected in simulation, deploying to the robot is very easy. Just replace the simulation subgraph with the hardware subgraph and deploy your application to your favorite Jetson device. Depending on your application, your goal generation may not be just a single node, but a collection of nodes, perhaps with artificial intelligence and some state machine. However, at the end of the day, they will need to supply a goal to the navigation subgraph, just like my goal generator does. To get started, download the nightly build from the Isaac website, untar it, and use install dependencies script as instructed on the documentation. Once you do that, you'll find the folder we have created for this webinar under Packages, Tutorials, Webinar_1. To run your first application, just type bazel run, Packages, Tutorials, Webinar_1, my goal generator test. To stop your application, simply hit Ctrl+C. Let's open up a new tab and have another look at the webinar folder. An Isaac application requires three kinds of files. While build file we assume is given, we will populate C++ files and application files in this tutorial. Now let's see what's inside these files. Open up the CPP and HPV files side by side. In the header file, we have the pragma, some includes, namespaces which we are free to change. We will derive our class from the following base class. Among others, we are free to define our own start and tick functions. As their names imply, start function is called once when we are starting the codelet, and tick function is called repeatedly. Finally, we need to register our codelet to be able to use it in Isaac applications. Moving on to the CPP file, we see that start function demands a periodic tick. Otherwise, both functions are left for us to fill. Let's print a hello world in the start function. And in the tick function, let's go ahead and print a warning. Just save the file and open the myGoalGeneratorTest.app.json. In this incomplete application file, GoToMockup is in its place, but it's missing myGoalGenerator that we just modified. So let's edit. Go to the graph section of the application, create a new section for the node. Let's name it, say, My Node. You're free to choose your own name. Then let's list the components. For now, we'll just add a single component, which is of type whatever we registered our codelet with. Isaac tutorials my goal generator. Then we also need to give it a name. Let's name it my component. There's one more thing we need to do. We told our codelet to tick periodically, but it doesn't know what the period is. So we need to configure it, just like how it's done for the go to mockup down here. So we are going to go to the config section. We'll start with the node name, which is my node. Then the name of the component, which is my component. And finally, the name of the variable we would like to set, which is tick period. Let's tick every 3 seconds. Great. Just save the file and we are ready to try this out. Let's run our application. Voila! You see that hello world is printed once because it's in the start function. However, tick is printed every 3 seconds. Let's go ahead and kill our app with Ctrl+C. Going back to our application file, we see that both goal generator and mockup are in place, but they are not connected yet. To change that, we need an edge. To see what mockup expects to receive, let's open up its header file. It seems like mockup is ready to receive a message of type goal to Proto. So in my goal generator, we are going to write Isaac Proto TX because it will be transmitting, and it's gonna be transmitting a type goal to Proto. And let's name it my goal. Now our codelet is ready to transmit a message of type goal to Proto. So we need to switch our attention to the CPP file to populate and publish it. First, we need to initialize it, and the way we do that is we say auto goal Proto, then tx, and name of the message, in our case it's my goal. We call init Proto. Then we'll set the parameters necessary for this Proto, but at the end we are just gonna publish it by saying tx my goal publish. To see what we need to set in this Proto, let's have a look at the definition of goal to Proto. It's defined in file navigation cap pnp, and when you use Isaac you'll find this all protos that are already defined, but you may need to define your own. It's quite easy, as you can see here, and it's well documented online. Seems like goal to Proto needs a pose, a tolerance, a frame, and a boolean. So let's switch our attention back to the CPP file, and let's start by setting the boolean to false because we don't want to stop. We want to set a goal for robot to move to. And for the tolerance that we see here, 0.1 meter should be a good choice. Then for the frame, let's publish in the world frame. And finally, we need to set a pose. And to set the pose, we can make use of a helper function defined in Isaac called toProto. And the way we use this is we first give whatever you would like to set it to. let's say we define a goal position at x equals 1.1, y equals 2.2, and then we tell to Proto what we are trying to set. Great. Now we need to include the to Proto that we use. It's defined in messages mat HPP. In the same folder you'll find useful to Proto functions, optional helper functions that you can make use of. Going back to the application file, now we are ready to fill in the edge. We are going to create one. Let's create a section, and we need to give a source and a target for a valid edge. And our source is gonna be my node. We are gonna transmit something from the my goal generator to the mockup. So the node name, component name, and the variable name, which we name to my goal. So let's go ahead and type that as well. And our target will be the mockup. So first let's have a look at what the name it's expecting to receive, and then we write the node name, component name, and it seems GoToMockup is expecting to receive a goal. That's the name it's expecting to receive. Let's save this. So we created the edge, but there is one more thing that we need to do. We need to make this node with my goal generator message capable, just like GoToMockup. And the reason why mockup is message capable is because it has a message ledger component. So by copying this over, we also made our node message capable. Now running the application, these two nodes should be able to communicate, and yes, voila, we see that GoToMockup is now receiving a goal in the world frame and this position, and it's printing that to the console. Let's Control C. This was a good step. We can then close the loop by receiving mockup's feedback in our goal generator. We need another Isaac Proto in my goal generator. So let's type Isaac Proto, and this time we need the RX, not TX, because we are receiving, and the type is going to be goal to feedback Proto, as we see in mockup. Let's name it goal feedback. Now our codelet is ready to receive. Let's process whatever is received in the CPP file. To do that, we write RX, name of our variable, and let's process only the latest new message. So this API will give us the Proto and also the 2 times publication and inquire times, which we are not gonna use in this particular example. Let's read arrival information from this Proto, and to see what we can read from the Proto, we can again look at the definition of the Proto. We are receiving 4 variables. Let's only read the arrival information for now. So we are gonna say feedback Proto get has arrived. And instead of printing this, let's show it on our website. under name arrived. If it's true, let's show 1, and if it's false, let's show 0. Now my goal generator is ready to receive. What's missing is an edge in the application file. Let's create another edge. This time it will be the other way around. Our source is gonna be the mockup. And the name is just let's check it out what the name is. It's feedback, and the target is going to be again the node name / component name, and we just named it goal feedback. And a tick period of 3 seconds is quite long for our goal generator, so let's make it tick with 10 Hz instead. However, this would clutter the console a lot because we print a warning at every tick, so let's comment that line out. And now we can run the application. To see the results, we are gonna go to site located at localhost 3000. It's localhost because we are running locally. And we see our channel here. Let's activate it and create a new plot with a name that we like. And we see that goal generator thinks, given the feedback, it thinks it has arrived. Remember we hard-coded the goal location here? Let's parameterize that. Doing so is easy with Isaac. So in the header file, we are just gonna write Isaac param. Then the type, it's gonna be a vector, just x and y, double values. Let's name it desired location. And let's give it a default value of 3.3 in x and 4.4 in y. After that, we can just replace the hard-coded values in the CPP easily, but by saying get underscore the name of the variable, desired location, and then we save it. And again, the default values are going to be 3.3 and 4.4, but we can overwrite that, for example, in the config section of our application file. So my component of type my goal generator, we are just going to go there and say desired location. Do you want to overwrite the default values by 9 in x and 25 in y? So when we run our application, we expect to see mockup printing these values, and yes, so those are the values picked up by our codelet. And what we can do furthermore is go on site, and we see our node here and the value parameter here. We can change it here, and it's again it overwrites what's in the application file. Note that whenever we change the goal position, arrived becomes false, and after 5 seconds it becomes true again. This is just the mockup behavior we put in place to test our goal generator. And for completeness, let's have a look at the build file that we never needed to touch. So this is what a typical build file looks like. We have the ISEC modules, C++ modules. In particular, we made use of my goal generator codelet module, and then we defined our application like this one, and that's where the name of the application comes from. We did it. Let's go back to the big picture to see what we accomplished. We now have a goal generator that sends a goal to mockup and it receives a feedback in return. Now let's see again what the folder has. So these are the 3 files we worked on together. We also supplied you completed versions here so you can compare and see if there are any differences. But if we go back to the big picture, as promised, it's easy to replace the mockup with the navigation subgraph and simulation subgraph and end up with this goal generator in simulation. And we also supplied you the simulation application. So let's have a look at both of these app.json files to see what's different. So on the left we have something very similar to what we populated together, and on the right we have the simulation. So in both of these applications we have the goal generator, and if you will look carefully, there is a high resemblance. The goal generator just generates a goal and receives a feedback. The difference is that instead of go to mockup, it talks to the navigation subgraph, and this is how we include a navigation subgraph which talks to the simulation subgraph. And again, ISEC makes simulation to reality very easy. So by replacing the simulation subgraph with the hardware subgraph, we can just make this app work in reality. And they use the very same navigation subgraph. They both have it. They also have the goal generator. In both cases, goal generator just sends a goal to the navigation subgraph and receives feedback back. The difference is though the simulation subgraph and the Carter subgraph. So whatever your hardware may be, you can put it in here, and then it should just work. Let's first see our goal generator in simulation. To do so, we'll use ISECsim, and please refer to the latest instructions on ISECsim documentation. This version that I'm using needs absolute paths. So we are going to do is get the absolute paths and change the JSON file here called Carter full. I'm gonna modify it so that both these paths are absolute and correct. Then we are ready to run our simulation. That was the bridge we modified, and then I'm gonna launch the ISECsim. I just downloaded the binary version, and the command I'm gonna use is this one. I'm gonna run Carter warehouse with given resolution, and we need to supply the full path to the JSON file we just modified. Let's launch it. And we'll look at the warehouse from robot's point of view. The goal will be supplied by the codelet we wrote together, and the navigation is done by the subgraph we included. So it seems to be working. We should see that it avoids this human. Well, the human also avoided us, so that's good. And it goes to the location that we put in the application config, which we can change here as we did in our test. Let's change the Y to 42, and as soon as we hit submit, we should see it's being picked up by the robot. So far so good. And this application seems like it's ready to be run on a real robot. This is one of the most entertaining parts. We are gonna deploy our application to the robot. So we'll use the deploy script, give the name of our application, IP address of our robot. We have Jetpack 4.2 installed on our Jetson, and our username on the Jetson is NVIDIA. So we are gonna use that. So this script is gonna build our package, cross-compile, and then rsync files to it. Then we can SSH to the Jetson to launch the app remotely. It's gonna be under deploy, my username, host username, and then the package is called goal generator real. So let's cd into there. And to run the application, we are gonna call the binary located at packages tutorials webinar 1. And the name of the binary is gonna be goal generator real. So we'll call that and run our application. And let's see what it's up to. So here we have the very same codelet, goal generator. I'm gonna change the Y position and submit. And Carter here will pick it up. Using the navigation stack, it will plan, avoid obstacles, humans, and control the wheel speeds to reach the target location as shown here on website. Carter is one of the reference designs we use for Isaac. While it uses a Lidar and Jetson Xavier, our waste sorting application that you can see here is carried by Kaya, powered by a Jetson Nano and a RealSense camera. Kaya uses artificial intelligence to detect and label objects to sort them. I would like to show you how to quickly get started with artificial intelligence in Isaac to develop cool applications like this one. Let's head back to our code base. Isaac provides you with powerful and easy to understand sample applications. In particular, let's run the YOLO inference app. On site, you'll see that Isaac is detecting various objects from an image. Instead of a fixed image, you could also supply a video from Isaac Sim or any other simulation of your choosing. Instead, you could also use YOLO Inference app in real applications as well, perhaps to generate some goal. The same sample folder also provides an application for training. You can either train in reality or in simulation. Let's have a look at another sample application. You will find that Isaac documentation is quite comprehensive, and it includes information regarding various applications. Course-to-Find Stereo Depth is a cool GPU-accelerated application of NVIDIA that uses regular images to estimate the depth information. Below you will find instructions on how to run or deploy this application. And also what to expect from site when we run this application. So let's run it together. And this is going to be my chance to wave at you. We encourage you to check the list of sample apps. we add more and more samples with each release. So let's summarize what we did together today. So we modified the C++ codelet, we wrote it together, and although Python codelets are supported in Isaac, we prefer C++ codelets for performance. Then we modified the app.json file that determines the application to reflect our changes in C++ codelet. We use website to track what our robot is up to and change the parameters as we desire. Then we showed that moving from test to simulation and from simulation to real is very easy with Isaac. We looked at a couple of sample apps together, and there are more if you are interested. So go ahead and download Isaac today and give it a try. Let us know what you think. We are looking forward to your feedback. Next release is going to be in 2019.2 in June. And although we focused on navigation in this webinar, what we really learned is how to use Isaac SDK. With this modular robot engine, you can tackle various robotic fields such as locomotion or manipulation. Just stay tuned for more. With that, I would like to thank you again on behalf of Isaac team for your interest. This is just the beginning. We will now answer some of your questions. Sorry we don't have time to answer all of them here, but please feel free to post them on our forum and we will follow up.
Okay, so we'll now take the questions. The first question we have is, what is the proper development practice for Isaac SDK? Write code on a PC with a GPU, compile it, and deploy it to a Jetson. And that's exactly right. That's how it's structured. You will need a host PC. You'll download Isaac SDK to it. And Jetson device will be at the edge, controlling the robot, talking to it, and you'll deploy your application to your Jetson device from the host PC. The second question is related. It's can we use the Isaac SDK directly on a Jetson without a host PC? And not currently, because we believe that having a host PC is easy and it will make it quite convenient for you to develop your applications. But once you confirm it works well in your tests, in simulation, when you're ready to deploy it to a real robot, you'll just use Jetson devices with the GPU acceleration on it, and you'll run your application.
And we got another question here. If we are planning to extend the Isaac SDK to manipulation and grasping objects. And so the answer to that is on our roadmap right now. And we will probably have some updates to share about that in the coming months ahead. So we are aiming to have some exciting demos around manipulation and grasping objects towards the end of the year.
Okay, the next question is, can you talk about the typical journey of a robotics developer from downloading the Isaac SDK to developing an application on Jetson? For people who are just getting started with edge computing and the value of NVIDIA. Okay, so this is a good question. This is exactly what we tried to illustrate in this webinar. Once you download the Isaac SDK, you'll just need to install some dependencies, which will be taken care of by a script that you will see in the documentation. And after running the script, you will be ready to go. You can just deploy your application. Once you know the IP of your Jetson, you will be able to just deploy the applications. We have some nice reference designs for you. but after you confirm everything works fine, you'll be able to just modify an existing application, or you'll be able to develop another application just like how we did today in the webinar.
Yeah. We got another question here also. It's actually a little set of questions. How does a codelet relate to a node, and how does a component relate to a node? So you might have seen these words in the webinar today when Oz explained how to create a custom codelet, and it was added to a node. So ISAC SDK uses a component-based design, which pretty much means that we create a complex robotics applications out of a lot of small modular pieces. And the lowest level of modularity is a node, and a node provides a certain functionality in the system. Now, you might be aware, if you have worked with ROS before, you might be aware of nodes in that context. In ISAC SDK, nodes are much smaller pieces than in ROS. So a typical ISAC SDK application has, for example, the Kata navigation stack has about 50 to 100 nodes. And every node has a small kind of purpose. For example, the global planner is a small node. The AQR planner is a small node. The node which decides where to go, like very similar to the one which Oz showed in the webinar today, is a node. And so component-based design then says that these nodes itself are not monolithic blocks, but they are made out of small components. And each component provides a certain functionality to that node. So it's essentially like a two-level hierarchy where an application is made out of nodes and a node is made out of components. And so typical components, ones you saw today, for example, is the message ledger that provides the message passing functionality. We are also working on adding more and more components which make this model of the component-based design more richer on ISAC SDK. And now the codelet is just a specialized form of a component, and that's the type of component you see the most. That's a component essentially which is periodically doing something. Not all components necessarily need to periodically do something, but that specific element is a component which is periodically doing something. And so the one you did today in the webinar is a codelet, periodically does something, it periodically checks if the robot arrives and then sends a new message to the receiver. So to summarize that, is an ISAC application consists of a lot of small nodes, and then each node is made out of a couple of components. And the most common component is a codelet.
Is the navigation stack that we used in this webinar modifiable? And certainly. So the navigation subgraph that we just pulled in is there just for your convenience. You can write your own navigation subgraph. You can modify the existing subgraph. We just created this abstraction layer, so you can just quickly get started with your applications by just defining different goals. But most certainly you can configure the navigation subgraph depending on your robot, or you can change the speed or whatever you would like, and you can change the behavior by modifying the subgraph or writing your own.
Yeah, and we got another question here that in terms of hardware support, if you look at ISAC SDK, we have, for example, on the LiDAR side, we support the Velodyne LiDAR right now. And there's other hardware pieces which are very common in robotics, for example, SIG LiDARs or from similar manufacturers like that. And so the question is if we will support more hardware over in the future. And so the answer to that is definitely yes. We are working with a couple of manufacturers right now to get support for LiDAR, more LiDAR and more camera types into ISAC SDK. So the next release coming up end of the month will already add more drivers, and then we will continue to expand that over time.
Another question is, instead of just navigating to a 2D X and Y location, are there any plans to have higher level functions? like, for example, floor coverage for a certain area like Roomba. And definitely, so this webinar was, we just wanted to develop something super simple with you online, but we already have different goal generators in Isaac SDK. One of them is, for example, is the patrol behavior. So you can say patrol between these locations on the map, and it will certainly do that. You could also do a random walk in the map. The robot navigates in. So all of that is already available to us, but we just wanted to show how easy it is to get started with Isaac. More complicated goal generators are definitely there for your convenience.
So there's another question here. If you need a GPU to use Isaac on a PC, and so the answer to that is actually it depends. If you use your host PC only to compile and then you deploy to the Jetson, Xavier, or Jetson Nano device, and you run your application on the Xavier or on Nano, then in that case you don't need a GPU on the host PC. Because you only use it to compile the source code, you cross-compile it, and then you deploy to the Jetson device, which has then a GPU. Now, if you want to run parts of your application also on your workstation, for various reasons, either because you just want to test something or because you want to do something in simulation, for example, then in that case, your application will be run on the host PC, and then you will need a GPU on the host PC also.
So a word about the two robots we showed today. One of them is called Carter, the two-wheeled one, where we tried our goal generator. And the other one we showed where we played a video was called Kaya. And one reason why we wanted to show you two robots is these two robots are very different. One of them is a differential base with two active wheels. The other one has holonomic wheels, 3 of them. Carter uses Jetson Xavier. Kaya uses a Jetson Nano, $100 super capable hardware. Not as powerful as Jetson Xavier, of course, but still very cheap and useful. And again, another difference is Carter uses Lidar, whereas Kaya has a real sense camera. The reason why we wanted to show both of them to you is to show how modular Isaac SDK is. So the same SDK, you can deploy it to any Jetson that you like, or the navigation modules that we have works on various different robots. So you can deploy it to your robot very easily.
Okay. We have another question here which says, is there a way to control the Kata Sim robot by clicking and setting the destination of the robot on a map in sight? So in the tutorial today, Oz showed you how to essentially send the robot somewhere in simulation or reality by sending the coordinates via a message. And so we have not covered that, but this is definitely possible. We have a mode for the Kata navigation stack where you can control the robot in various different ways. You can, for example, set a patrol codelet, and it will randomly pick goal locations and drive the robot from one location to the other. It's kind of useful to just test the stack. And there's also one mode where you can click on the map in sight and you can position the goal position of the robot and its orientation. You can define it, and then the robot will drive to that. So we're doing this via interactive markers. It's not covered in the tutorial today, but we will in the future probably provide more information also about like a deep dive into the navigation stack and how to control the robot via the navigation stack and discuss that in more detail. But just for today, if you look at Isaac SDK, there is a Kata app, and if you run that Kata app, you will find a node somewhere which says goal, which sends the goal, which defines the goal mode. and that can be switched between waypoint and pose.
There's a question about Kaya's mapping abilities, and Kaya can certainly generate maps. For mapping, we use third-party software. Currently, we support Google's Cartographer and OpenSlam's G-mapping algorithms. You can plug in other mapping algorithms or develop your own, whatever is convenient for you. And Kaya can certainly map, and we'll provide this reference application with the next release coming in at the end of June. However, a word on that is it's easier to map with a LiDAR because you get 360 vision. And Kaya only sees, it has a limited field of view. It only sees front. But yes, you can still map your building.
There's another question here which asks, will there be reinforcement learning tutorials released after the release of Isaac Gym? So the answer to that is probably. We will add, over time, more and more tutorials. And the things we plan to cover are the navigation stack, working with simulation. Today you also saw a brief kind of look into how to do machine learning in the context of Isaac, and that's definitely something we will expand. And there's a lot of kind of more classic machine learning to be covered, like how do I train an object detection neural network, how do I train a stereo depth estimation neural network, and so on. And reinforcement learning is definitely a very exciting topic in terms of robotics. And I think we're pretty close to sharing some exciting things about that in the future.
There's a question. One of our viewers is interested in getting a robot. And as NVIDIA, we don't actually sell robots, but these are just reference applications to illustrate the Isaac SDK. We want to show that it really works with these reference applications and help you get started with your own robots. However, we make it easy for you to manufacture these robots yourself by documenting how we manufacture it by the parts. For example, Kaya, you can print all the 3D parts yourself, and everything else is off-the-shelf products. For example, the battery is actually a drill battery. So what NVIDIA is telling you is the Jetson product, the brain of the robot, and we provide Isaac SDK with it, so you can develop your robotic applications. But we don't sell the robot itself, but it's super easy to do so. Get it yourself.
I have one question here about the simulation, and it basically asks that if I have my own robot model, which is not Kata, how do I get that into simulation in Isaac SDK? So that's of course a very important question, and I think we will need more tutorials to answer that in detail. But in principle, it's actually quite easy. You need a 3D model of your robot, which you can import into the Isaac Sim simulator, and then inside the simulator, you need to set up your robot to essentially specify where's the center of rotation of the robot, depending on your drive model, what's the radius of the wheels, what's the distance of the wheels. You need to set up the collision models of the wheels itself, and then that's kind of on the physics simulation side, so to say. But then starting from there, if it's, for example, a differential base, it is pretty much exactly the same as the Kata simulation and the Kata navigation stack. If it's a slightly different base, then it might depend. If it's a different drive model, then you might need a different drive model.
There's a question about LiDAR, and the question is, can we change the LiDAR used in this webinar? And the answer is yes. You can use any LiDAR of your choosing. You can write the driver for it if it doesn't exist yet, and you can plug it into the application to replace. You can replace any components, any nodes in this webinar, modify it or write your own. And as Kaya reference application illustrates, you don't have to have a LiDAR. It's just one method to navigate, to see the world around robots.
There's another question here which basically states that LiDAR has some limitations in terms of navigation capabilities, and if there's ways to basically solve that, or how can the system be more customized to solve that. And so I'd like to answer that in two ways. So on the one side, we will, in the next upcoming release and then also the release after, provide more capabilities to do camera-based obstacle avoidance, so integrate more camera-based perception into the navigation stack, or more like as a complement to the navigation stack. And so that's then essentially a way where you get really into the details of what is your specific application, what is your setup for your robot. Do you have one LiDAR? Do you have two LiDARs? Do you have a 3D LiDAR or a 2D LiDAR? Are you using the LiDAR only for safety? Are you using a camera for your main obstacle avoidance? Are you driving backwards a lot? And so then ISAC SDK should give you, so that's the purpose of ISAC SDK. It gives you the ability to map that robot essentially into a robot application, and you have all your drivers running, and you have different object detection or obstacle avoidance algorithms running. And we will provide some features around camera-based solutions for that. Now, if you want to go into the existing LiDAR navigation stack and essentially modify things, so currently the navigation stack is, we don't publish the source, we only publish the binaries. But this might change in the future, and we might decide to open more and more of the source. And especially also for partners who are collaborating more closer with us, we also provide the source for that.
There is a question about the message passing that we have. So we make use of CAP-PNP, which is a super optimized, super fast message passing that we are using. You can find more. We didn't go into the details of it in this webinar, but you can certainly find more information about it online and in our documentation. You'll see that it's very easy to define a message proto, pass it around, populate and read from it. It makes the whole program very high performance and makes it very, very scalable.
And we got another question here about the ecosystem, essentially. How can other people contribute drivers for various hardware pieces and then share it with other people? So in the upcoming release, we will move to, so we will just, we restructured the code base a little bit, the ISAC code base a little bit, and make it much easier to provide a modular piece, like for example, for like a driver for a new hardware piece, and to provide that completely separate from the ISAC SDK. And we have two examples where we kind of show how this can be done very easily. And we will share them together with the next release. And then that is essentially giving other people a very easy to follow, so to say, cookbook on how to create a driver for a certain hardware piece.
This will be the last question, but please keep them coming on our developer forum, and we'll be happy to answer all of them. The last question is about Kaya. Does Kaya use G-mapping through RealSense? And Kaya, that's correct. We use G-mapping through RealSense, but we made it so modular that you could plug in, for example, you could put a cheap LiDAR instead of RealSense on Kaya, or you could use cartographer instead of G-mapping, or it doesn't need to be Kaya, a different robot. So all these parts are modular, so you can plug in. So the G-mapping algorithm doesn't actually know we are using a RealSense camera. We just have a driver for RealSense. We get data out of it, we convert it, and feed it to the G-mapping algorithm, for example. So it's super flexible. You can change any parts of this flow.
Yeah, so one last word. Ozaz already mentioned it. We have a forum, and you can answer questions. You can ask questions in that forum, and we're answering most of the questions there. So if you have more technical questions, please join us on the forum and ask your questions there.
Thank you all for joining today's webinar, and thank you, Oz and David, for presenting. As I said, there were a ton of great questions that were submitted we weren't able to get to, so post those on the forum, and we'll continue to answer those there. We have recorded this presentation, and we'll have it available shortly on demand. You'll also receive an email with a link to that information later today. And don't forget to become a registered developer for the NVIDIA Registered Developer Program. You'll get access to the latest news on products, software, events, and more. And thank you all for joining us today.